my talk is transients variables that you have modeled or are searching for and how to find them, especially in large surveys. And this is a talk based on Fink, who is processing basically data from CTF and Rubin. So the Veracity Rubin Observatory will be like this huge 10-year video of the sky, of the southern sky. It's up to magnitude 24. I'm extremely biased to extragalactic transients, but I checked, we can find exoplanets for the people interested in that. But I'm going to tell you a more extragalactic version of this. The challenge here is that we're going to find up to 10 million detections every night for 10 years. So the question is how you go from 10 million detections to getting your different objects. That could be superluminous supernova, it can be weird supernova, it can be kilonova, it can be TDEs, whatever you want, including exoplanets that I have no expertise whatsoever. So before Rubin, which starts next year around 2025, the 10-year survey, we have CTF. This is Switchy Transient Facility. Basically, is like the precursor for Rubin. It's up to 1 million detections every night. So here I'm showing you real events from CTF. This is a variable star. This is a little bit a supernova next to a host galaxy. And we also find things like satellites or asteroids blinking in our images. So that encompasses around actually 300,000 detections every night. And we have been receiving since 2019 all this data. So the challenge here is we have this huge amount of data and we're trying to find our little fish here or needle in the haystack, which is probably varying or fading or whatever it's doing in your models. So how do we go from 10 million detections to finding your little fish? Well, that's where Fink comes in. So we will be receiving, we're one of the official brokers for Rubin. We will be receiving every night in real time, seconds after an image has been taken in the telescope, all that data. So its infrastructure is deployed in France. We will have a mirror in Australia, hopefully. But the idea is that we get all those 10 million alerts, actually thousands, 100,000 per every couple of minutes. And we start with a positional cross-match with catalogs. These can be catalogs that we really know well, like Sinbad, or maybe variable star catalogs. You can also have surveys, like we have a partnership with SWAM, who will be doing gamma ray in the future from space, but we also cross-match with footprints like gravitational wave footprints, etc. Then we have all that information of cross-match, and then we go to the next thing that is features, whether it's rising in magnitude, fading, what's the probability of it being a one supernova, kilonova, etc. And a lot of this is based in machine learning. And I'm going to tell you a little bit why machine learning is so powerful. One, because it can handle very large data sets. And second, because you can input all the diversity of your models into these decision algorithms and try to find one of your objects. And then with all that information all together, you can actually decide a filtering. It can be, I want things that have a high probability of being a kilonova, but are actually in blue galaxies, because I don't know why you want the blue galaxies. And then you can get it either automatically for telescope follow-up or via our web portal here. Even in the telephone, we have an app, and you can get it in your Jupyter Notebook, terminal, etc. So what I'm going to do is I'm going to tell you the 101 of how I think we could find the things that you are modeling. And I have 3 cases. Now, this is not exhaustive. I want to hear what you think. I think one of the things that we can do is search for specific models you have developed. The second one is to find borderline classes and see if one of your models fit one of those borderline classes. And the third one is what we call anomalies, which is super hard to define because what is anomalous for me is not anomalous for you, probably. So for me, an exoplanet probably is an anomaly, while for you, probably is the most exciting thing in the world. So searching for specific models. Let's say you have generated this electron capture supernova model, you have some diversity of parameters, etc. You can go and get those 10 million events per night and try to do template matching. or template fitting. Can you do that with 10 million events every night for 10 years? No, unless you have some quantum computing power that I don't know about. But you can start searching like a filter to get your favorite model, maybe, because if you know if it has a decrease rate of 0.4 magnitudes every day, maybe that will constrain it. Maybe if you have like a galaxy that looks like this, and you can correlate it. But probably the most efficient way of doing it, that you generate a lot of diversities of these, and then we can train a machine learning algorithm. This is what we did with Kilonova. Actually, these are two works led by a student, Biswajit Biswas. So we took a lot of models of Kilonova. We have only one confirmed till now. So we took a huge variety, and he trained a bunch of two models actually, with a lot of Kilonova models to try to find them in our data. So these are some of the ways that he fits the data in CTF. We actually will get 2 or 3 detections at most. It's very sad. We will see what's proven. But this is a very good way to get in a match with your potential model. These work so well that we are actually using it for follow-up around the world with the collaboration Grandma. This is all the telescopes around the world that they have. And we filter according to this probability of detecting this kilonova in the light curve. And then we do other things like cross-matching with host galaxies or searching how they evolve. Until now, we haven't found a kilonova. If not, this will be a Nature big paper. But we have found a lot of things that can resemble kilonova in the data, like CVs, which are the bane of my existence, asteroids, also bane of my existence. But you can see here how good the light curves that we get if we try to coordinate. Also, in the right, I put some of the histograms of the strengths of doing machine learning against cross-matching with galaxy. So you need to be careful that there are different ways of thinking to get the same objects. And this is something very important when you think about these big data sets. Now, that's the first approach. The second approach is, well, maybe you're searching for something that may be borderline, explaining a continuum of class instead of discrete classes. So you can search for borderline classes. So basically, you create a filter to get what is a, for example, normal type 1a and normal core collapse, and try to search things in between. There's another way of doing this, which we're trying is, well, when you do machine learning, if you do supervised learning, you have a set of known events, you train an algorithm with those known events, then you apply it to unknown events, which are the ones that you just received, and you select the best, your target, type 1a, core collapse, kilonova, whatever you want. There is an interesting way of closing this loop, which is called active learning. So you basically now, instead of selecting the things that the classifier is most sure, you take the ones that is most unsure. Those things are around 0.5 probability. I don't know what it is. And send it to the telescope to get the typing and the classes and characterization. And this is what we have been doing with active learning with type 1a supernova, early type 1a supernova. And we have been following up here in Australia. And you can see some of the light curves. And what we have found is a lot of these early events that we only have like 3-4 detections that look like type 1a supernova, but the classifier is not really sure. Some of them are type 1a supernova, but some of them are weird type 1a supernova who are evolving faster than they should, maybe have an environment that are weird. Sometimes we get CVs, of course. Of course, we have other core collapse supernova, but some of them have lines that we're not really sure if they're completely this type or the other. So that's super interesting. Now, the third thing is searching anomalies. So everybody's super excited about the unexpected. But if you're searching within 10 million of events per night, 1 needle in the haystack, it's very hard to define what is an anomaly. And of course, once you find them, we need the models to get them. So one way we have been working is there is a group in Think that has done this isolation forest machine learning algorithm, trying to find weird things. So the first night we deployed the algorithm, we actually found this object, which I didn't think it was so incredible, but actually it's a very, very weird star flaring. Actually, I think there's only 3 or 5 in the literature. So that was pretty cool. But then again, for me, a star that is flaring, that's not what I'm searching for. So we're creating a recommendation system like Netflix or YouTube has a recommendation system of what interests you, where now with simply putting thumbs up, thumbs down, you can create your own mechanism to get the anomalies that actually interest you. So I don't want stars. I want things that look like extragalactic, like look like supernova, TDEs, kilonova. So I basically retrain the model until it learns what I want. So there is a Telegram bot if you want to take a look at that. Meanwhile, we have found weird things like this one that raise a couple of magnitudes within 2 days. Maybe a TDE, maybe a CV. We don't know yet. We got a lot of observations around the world. You can see all these observations and follow-up. We still don't know what it is. Some people say it's a CV, some people say this is not a CV, some people say it may be a TD, some people say this doesn't look like a TD. So what it is, we're having fun. If you have any ideas, I'd love to talk with you. So to finish up, we have different science interests. We want more people working in Think. These are some of the things that we have. We have also connections with other data sets. These are things that are maybe more closer, solar system objects, etc. But this is all community driven. And I think right now what we need to think is this is a great opportunity to find whatever you're modeling. The challenge is the amount of data. All our data is public. So we need to start preparing now to actually find those objects. And if you have a model, let's find a way to predict how they're going to look in the optical place, because sometimes I don't know what to expect, and then we can figure it out. Thank you.
So I have a question to the active learning approach. If you can go back to the slide, perhaps.
Yeah, sure.
So
Probably this one.
yeah, exactly. So the thing is that the machine learning algorithm will always issue some prediction, right?
Yes.
So how will we know that this is an unknown event? How will we know that the predictive model is uncertain? So are you training a model that makes probabilistic forecasts and then having low probability?
Actually, not low probability, because I usually train in a binary classifier is the easiest way to train. So let's say that you train cats and dogs, okay? The probability of being a cat or being a dog. But it gives you like a 0.5% probability. So it really is not sure between the two of them. So those are the events that we're actually tagging to get a spectroscopy.
And then you have more data. And then for each type of transient, you train a separate algorithm.
So
even though type 1A, step 1B, step 1C, and so on.
We don't have active learning loops for all the types of algorithms right now. We only have some algorithms that have been developed for the active learning loop in type 1A supernova and anomalies for the type B. That doesn't mean we cannot do with other transients. It's community driven. So right now I'm interested in this, so we are doing this.
And for training, you use just spectral data or light curves?
It's Likert. So usually our simulations of transients for type 1A supernova, except for this model, we use around 30 type 1A supernova with a spectra or something like that. It depends a lot on the problem that you have. It can be either simulations or it can be real data.
Okay.